So this is part 3 of our acceleration or accelerated motion tutorial. This is a short one where we're going to tie up loose ends about concepts associated with acceleration. The previous tutorial we got very mathematical, looked at the algebra and some of the graphical, and in the first tutorial we introduced the concept of acceleration and how to interpret position time graphs that are curved and velocity time graphs that are linear. Okay, so the first thing we're going to start with is to make sure we're clear what it means to accelerate. For most people, when we say accelerate, they automatically think we're going faster and faster, and that certainly can be the case. Okay, so that's one way it means to accelerate. But we've also said it can all mean to go slower. Okay, so when you brake, we might call it deceleration, but you're technically accelerating. You're changing your velocity. And the last one that you need to be aware of, which we'll investigate mathematically later on in the year, but is just as important, is change in direction. Okay? So you could be going the same speed around a curve, but you're continually accelerating because your direction is continually changing. And that has important consequences, like I said, we'll talk about later. In terms of vocabulary, deceleration, which is a common term, does always mean to slow down. But as we'll see in a minute, negative acceleration, acceleration in the opposite direction, does not necessarily mean slowing down as well. It sometimes can. So let's establish a relationship between direction of acceleration and direction of motion, which is about velocity. And this came up in our practice with the graph. So I'm going to refer to a hypothetical graph right here, where I have something occurring at time 0, and we have, if you will, the velocity graph looks like this, going down, and then it's a level, and then it starts rising again. And so I'm going to break this up into 4 segments, A, B, C, D. I'm going to ignore the flat segment right here. Okay, so rather than calculate values, what I want to look at is what are the directions of the acceleration and velocity in each one, and so we can understand the relationship about directions of each. So in the first case, our velocity is positive because we're in the positive quadrant, but our acceleration is negative because our slope is negative. And if we were to describe the motion, we would say slowing down. We're going from moving to a velocity of 0 right at this point there. Okay, if we take the next segment, where we're below the x-axis, our velocity is now negative, but our acceleration is negative because the slope hasn't changed. That's our acceleration, and we're in the negative quadrant. But in this case, if we describe our motion, we'd say we're speeding up. Okay, and if we go to segment C, if you will, our velocity is still negative because we're below the x-axis, but our acceleration is a positive slope. So we have a positive acceleration, and we would say we're going from a speed to 0, so we are slowing down. I'm just going to write slowing here. And then lastly, in this last segment, we're going from 0 all the way up to here. Okay, so we're gaining speed. And if we look at our velocity, we're now in a positive quadrant, and our acceleration is still positive. So we can look at this. Negative acceleration over in this area is slowing down, but negative acceleration down here is speeding up. And we have the opposite on the other side of things. So how do we make sense of this? Well, if you look closely, you'll see a pattern. Okay? And basically it's this. When we're speeding up, the two cases, look at the signs for your velocity and acceleration, and you'll notice they're both the same. So in the quadrant right here, we see that we have a negative of velocity, negative acceleration. In the quadrant right here, we see we have positive and positive. So in both cases, we're speeding up. And then if you look at the other two situations, the slowing downs, we see that the opposite direction for the velocity and acceleration. So what it means is if I'm moving to the left and accelerating to the right, I'm slowing down. If I'm moving to the right and accelerating to the left, I'm slowing down. If I'm moving to the left and accelerating to the left, they're both in the same direction, we're gaining speed. So we can summarize that very simply by saying if the direction of motion, which is really velocity, is the same as the direction of acceleration, then we're going faster. And then if the direction of motion is opposite the direction of acceleration, then we're going slower. Okay, so that's important to remember. Okay, moving on to the next concept. oh, I'm sorry, there's an example here. So if a car is moving 30 kilometers per hour, that's a velocity, westward, and accelerating 6 kilometers per hour per second eastward, then it is, well, let's see, are they in the opposite direction? Yep, so we are slowing down. So to say that we're accelerating 6 kilometers per hour per second eastward tells us nothing unless we know something about our initial motion, which was westward. In fact, if you did a little algebra, we could figure out that it would be stopped in about, or exactly 5 seconds, right? 5 seconds, 6 kilometers per hour per second gives you 30 kilometers per hour. But that's something we'll worry about later. Okay, now we're going to switch it up a little bit to really give you another way of distinguishing between velocity and acceleration. Okay, we interchange them very often without thinking about it, but I'm trying to make clear they're very, very different measurements of motion. So let's go to amusement park ride. We plan on going there to Darien Lake sometime in the spring. Many people spend a good amount of money at Disney or Darien Lake or even Seabreeze, not just for the great food or the great prizes you can win, but for the thrills in the ride. Okay, so why do so many people like to go on roller coasters or similar type of rides? They like the feel. They literally feel something called a thrill. There's a psychological thrill and there is a physical thrill. You can feel it in your body. So let's say you want to go on a ride that gives you maximum thrill. What would you want about the ride? Well, common sense would say we want it at a greater speed. Okay? The faster the ride, the greater the thrill you feel. Or if you stop and think about that, in other words, if you answered yes to the above question, then we could ask, why don't we feel a constant thrill of the Earth by virtue of it moving 60,000 miles per hour around the sun? Right? Every day of our life since we were born, we've been moving around the sun. That speed is around 60,000 miles per hour, yet you don't hear people raising their arms going wee, wee, wee all the time from that thrilling ride. So what is that telling us? It's not that we're used to it, because when you're first born, then that would be, whoa, quite a thrill. That might, well, maybe that's the reason why we cry. But rather, you realize that it is impossible, okay, to feel speed. That's a really weird concept. If you've ever been in an airplane and you're just sleeping or relaxing, you can't feel the plane moving, let's say 600 or 700 miles per hour. In fact, if you woke up and you didn't hear the engines, you wouldn't know whether you were not moving or moving at a constant speed. Okay, so it's the same thing with an amusement park ride. When you're on an amusement park ride, what you feel are changes. The more sudden, the more thrill. Changes in motion. In other words, amusement park rides are all about acceleration. Okay, so when that roller coaster goes from very fast to very slow, you feel it. When it goes from slow to fast, you feel it. But most often what you feel in a roller coaster ride or an amusement park ride is a sudden change in direction. When you're going from up to down. To me, that's the most thrilling part of a roller coaster ride. When you're going from down to up, you feel like you're being pressed into the seat. When you go around a curve, you feel like your body's thrown one way or another. So you can literally feel those. So a very important distinction. Your body cannot feel or sense velocity, but it can feel or sense acceleration. Okay, so the last thing I'd like to talk about gets a little bit mathematical. All right, and that's looking at acceleration time graphs one more time. So I have a situation here where an object is moving with a steady acceleration, not a steady velocity. So if we want to describe its motion, all right, given that its initial position is 0 and its initial speed is 0, we would say, all right, well, how do we break this down? If this is acceleration right here and this is time. Well, we have a positive acceleration. So a positive acceleration, we will assume means going faster here. You could make the argument, well, we can't go less than 0 because we're that. So we're going to say we're going faster. Okay, and since we start at position 0 and we have we'll assume a positive velocity, we can say going faster in the forward. But that second part, the forward part, one could argue that there's not enough information for, but we'll just assume the common sense. Now, the reason I bring this up is we can do something mathematical with this, and that is take the area under this graph. And so if I look at the first 10 seconds of that, I drop it down to here and I'm bound by the x-axis, I see that we are basically sweeping out a rectangle. And if we find that rectangle, which is just base times height, the base is time, the height is the acceleration, so acceleration times means something in physics. Okay? In fact, if we look at the definition of acceleration as change in velocity multiplied by or divided by time, and we rearrange that, we see that acceleration times time is nothing more than a change in velocity. Okay? So we've seen the area under a velocity time graph gives us displacement. Now we're seeing area under a acceleration time graph gives us a change in velocity. So for this particular graph, the change in velocity, which is the area, is the acceleration, which is given as, I can barely read that, I think it says 2 meters per second, multiplied by 10 seconds. So that's 20 meters per second. That doesn't necessarily mean how fast you're moving at the end. It just means we've changed 20 meters per second in that interval. Okay, so that concludes our discussions on this concept of acceleration. If you have any questions, be sure to ask.